All right, so let's see how this goes. I'm going to try to, I couldn't get the camera in the closer position that I wanted to, but let's see if this works. I want to start by reminding you that what we've done in modal analysis is to take the equations of motion, which are mq double dot, maybe I should write it a little bigger, plus cq dot plus kq, right, equals to b2 ft, and we've taken these equations and we've made essentially the substitution, right? I won't go through the whole thing, but we've made the substitution of expressing the coordinates q as being phi y, where y are the modal coordinates and these are a function of time. This is a function of time. Q are the mode shapes, right? And now this matrix, which contains the eigenvectors, has columns which are phi1, phi2, etc., right? And we recall that they are the solution of k times phi j is equal to m times phi j times lambda j, right? Now, this is the equation of motion in coupled form. We introduced this transformation. We went through the steps 2 times, but we introduced this transformation. This matrix contains as columns the eigenvectors, and the eigenvectors are the solution of this system of equations, okay? When we do that, this equation becomes, the equations of motion becomes diagonal, and the amplitude of any mode is solved from the equation yj double dot plus, again we have in the derivations 2 omega j times the damping of mode j times y dot plus omega j squared yj equals, on the right side we had phi j transpose times b2 times the time histories ft. Okay, we did an example in class in which we solved this for 3 modes or something like that, added them together to get the solution. So basically modal analysis is essentially recognition that the key equations, of course, is this one, right? This is the key equation. The key equation is that the displacements vector, instead of expressing them in geometrical coordinates, we make this linear transformation, and instead of speaking of q, we'll speak of y. Of course, we can always get back to q because of this relationship. The y's have the advantage that the q's don't have, that they can be solved one at a time, right? By solving single degree of freedom equation. Now, one thing that we may have is we may have a structure, let's say this to fix ideas, right? Again, our typical shear building, and we have, let's say, 3 degrees of freedom and so on. Well, what if the problem is not that there is a dynamic load, but the problem is that there is an initial condition? Well, the solution for an initial conditions that you might expect, it's still the same thing. You still get to having to solve this equation, but now this equation must have some initial values of the amplitudes y, okay? Now let's pursue that situation. If we have an initial condition, that means that we know Q0, right? Now you would say, okay, so Q0 is the displacement vector at time 0. That must be equal to phi, right, times y at 0. So the initial conditions in the y coordinates are related to the initial conditions in physical coordinates this way. And the same thing follows with Q0 dot, right? If we have initial velocities, those initial velocities can also be written like this, right? So the initial velocities in modal coordinates are related to the initial velocities in physical coordinates this way. Now, if we follow the math, then it's quite evident, right, that y0 is just the inverse of the model matrix multiplied times the initial conditions q0, and that the initial velocities y0 dot are, again, the inverse of the model matrix multiplied times the initial velocities. Okay, I'm going to erase here. And I guess I don't need this. So it leaves us this thing. So the point, now why is this unacceptable in this form? It's unacceptable because in order for me, or for us, to calculate the initial conditions in the model domain, we again would need the inverse of the model matrix. And we don't want to deal with the inverse of the model matrix because the whole point is to not have to have all the modes. If the system is big, this matrix is large, and we certainly don't want to compute all the modes, neither do we want to invert the matrix. So to avoid that, we do exactly the same thing as we have already done, right? To get rid of the phi to the minus 1 that was on the right side, we can simply say we've already shown that the modes can be mass normalized, and that if the modes are mass normalized, then this result is the identity. So from that result being the identity, we can certainly multiply times, post-multiply times phi to the minus 1, and again, we've already seen this before, phi transpose times m is equal to phi to the minus 1, and therefore we conclude that the initial displacements y0 are equal to phi transpose times the mass matrix times q0, and the initial velocities are equal to phi transpose mass matrix times q0 dot. Okay? Now, that solution right here, not only does it avoid or eliminate the need for us to invert this matrix, but also no longer requires that we have all the modes, because let's consider the case where we only have let's consider writing this y0 like this. So this would be the y0 on the first mode, the y0 on the second mode, the y0 on the third mode, etc., right? On the right side, this matrix is the phi1 transposed is the first row. Then this is the phi2 transposed is the second row. The phi3 transposed is the third row, etc., right? Then comes the mass matrix, and then comes the initial conditions q0. So if I multiply the mass matrix times q0, that is just a vector, right? Therefore, this is the same thing as saying that y01, y02, etc. is equal to phi1 transpose, phi2 transpose, etc. multiplied times this vector, right? Here. So you can see that if I need to calculate y01, all I need to know is phi1, because phi1 transpose times this vector is y01. If I want to do two modes, I need y02, and that's phi2 transpose times this vector, and so on. So we can say then that our initial conditions are Y0 in mode J is just simply phi J transpose multiplied times the mass matrix multiplied by Q0, provided, of course, that the modes are mass normalized. Mass normalized. I didn't show the exact thing, but it's obvious from the parallel result that Y dot 0 in mode J is just phi J transpose times the mass matrix times Q0 dot, right? With the modes mass normalized also. So this is the end of the story as far as initial conditions go. Now, I mean, as far as the math goes. Now, in case it serves any purpose, let me actually sort of draft an example right here as we go that perhaps might help a little bit. What I have is I have the laptop open in the desk. You cannot see it in the camera, but I have it here nearby. And so I can, I'll be stepping in and out a little bit and, how should I say, and doing the calculations over there that need to help me out. So for that purpose, let's see, let's do the simplest possible case, or not. No, let's do one with 3 degrees of freedom. So let's say in the example that we have this situation, 1, 2, and 3. And let's say that this system has a stiffness in each story. K is 100. And that in each floor the mass is, I don't know, 1, 2, 1. Okay? No, let's not make the stiffness 100. It's going to be a little too low. Let's say the stiffness is 300. Interstory stiffness is 300. So this is the building. And let's assume that the situation is this is degree of freedom 1, this is degree of freedom 2, and this is degree of freedom 3. And we have an initial condition which is, I don't know, let's say we have something that says the first floor has a displacement of 1 and the other 2 floors have a displacement of 0. We want to know what is the vibration of this building for time after t equal to 0, if at t equal to 0, these are the displacements, and let's say that the velocities, because they are needed also, are 0. Okay, so we have an initial displacement vector and an initial velocity vector of 0. Okay. Now, what we need, of course, in order to do any problem in modal analysis, the first step is to calculate the modes. That is the transformation that will get us to the uncoupled system of equations. In this academic, very small problems, there are 3 modes. It's obvious that I can calculate the 3 modes right away. But you can think in your own mind, if instead of being 3, there were 3,000, we could set out to say that we want to calculate 20 modes. And that we're going to do the solution truncated, not the exact solution, but we're going to add 20 modes. In this particular case, I guess a truncated solution would be based on either 1 mode or 2 modes, because by the time we add 3, we got everything, and so it's the exact answer. All right. So the first step, we need to form the mass matrix, and for a building like this, it's just 1 to 1. It's just a listing of the diagonal, of the masses in the diagonal. And we need to assemble the stiffness matrix, and that's going to be 600 minus 300 and 0. And then we move this level, and that's going to be 600 and minus 300. And then we pull the last one, and that's going to be 300. So this is the mass, and that's the stiffness. I now allow me to get out for a second here. I'll continue to speak even though you cannot see me. And I am writing down on the screen of my laptop the matrices that are there. So diagonal, 1, 2, 1, and the stiffness equals 600. Okay, done. So I got the mass and the stiffness. Now I'm going to calculate the eigenvalues of m to the minus 1k. And the eigenvectors, okay? And I've calculated, now I'm checking to see if they are mass normalized. And I see that the program in MATLAB has given them to me mass normalized right away. And therefore, I am going to carry the laptop in my hand here now and write the modes right here. And then I'll erase over there. So the first mode proved to be, I'm going to use 2 digits, 0.28, 0.52, and 0.62. The second mode is minus 0.51, minus 0.30, and 0.75. Okay, the third mode is 0.82, minus 0.37, and 0.25. Okay, now I think I can erase this, don't need it anymore, and well, you already have it, so 1, 2, 1. So I'm erasing this, right? Now, we want to calculate the initial conditions, and so we say, okay, what is y1 on the first? What do I want to say? Yeah, what is y in the amplitude on the first mode? I'm trying to use the same notation. I guess I called it y0 in the first mode. That would be phi1 transposed, which would be 0.28, 0.52, and 0.62, multiplied times the mass matrix, which was 1, 2, 1, and then multiplied by the initial displacements, which were 1, 0, 0. And if we do that multiplication, we would get this. A, the first vector, transpose, times the mass matrix times 1, 0, 0, and we get 0.28, 18. So this is equal to 0.28 using 2 digits, okay? If we do the calculation on the second mode, y02, we would simply have minus 0.51, minus 0.3, 0.75, and then the same mass matrix 1, 2, 1, and the same initial displacements 1, 0, 0, and the answer in this case would be or will be minus 0.51, rounding to 2 digits. And if we do the same for the third, and I won't write it, we get 0.815, which 0.82, I guess. So I can say y0 on the third is equal to 0.82. Now, for the velocities, because my velocities are 0, of course, I have y0 dot in the first mode is 0, y0 dot in the second mode is 0, y0 dot in the third mode is 0. Otherwise, I'd have to do the same multiplications, right? Now that we have that, I will store these values over here. Let me just say that the y0 vector which is the ordinates of this thing, was 0.28, minus 0.51, and 0.82. Keep them there, and then erase this. Okay. Guess we can get rid of all this too. I guess I can get rid of this too. So we have our amplitudes there. Now, the modal equation is for any mode, y double dot, right? Let's say j plus 2 omega j, the damping j, yj dot, plus omega j squared yj equals to B2 phi j transpose B2 ft, but if there is no loading, it is equal to 0, right? Now, this is just a single degree of freedom, and when we have the first mode, we have this amplitude. When we have the second, we have this amplitude, and we have the third, we have this amplitude. So, in order for me to say it as quickly as possible, say the damping is 0 in the first mode, for example. Because notice that I can choose the damping ratio now as any number I would like in any mode. So let's say I take the first mode and I say the damping is 0. For if I say that the damping ratio of the first mode is 0, that means that the equation is y double dot plus, right, omega 1 squared y1 equal to 0. And we know that the solution for this is y1 of t, right, is equal to what? Is a sine plus b cosine. Should we go through the whole thing? Okay, let's go through the whole thing. Is equal to a sine of omega 1t plus b cosine of omega 1t. And then if we say at time t equal to 0, well, okay, and y1 dot of t would be equal to a omega 1 cosine of omega 1t minus b omega 1 sine of omega 1t. Taking time equal at t equal to 0, right? We would say now, what is at time t equal to 0 y1? Well, it's equal to 0.28, right? Therefore, 0.28 is equal, sine of 0 is 0, cosine of 0 is 1. So that's b, right? Now, at t equal to 0, the velocity is 0, so we can also say that 0 is equal to a omega 1 minus, that's 0, right? Therefore, we conclude that a is equal to 0. So the solution then is that y of t for the first mode, right? Y of t of the first mode is just simply 0.28, right, times the cosine of omega 1t. Now, omega 1 is the natural frequency of the first mode, which I didn't copy when I was solving it, but I can just simply look at it right here, and I see that it is I see that it is 6.60. So omega 1 proved to be 6.6 radians per second. So y of t, y1 of t is equal to 0.28 cosine of 6.6 t, right? Now, if we, in order to save a little time, I could have damping on the second mode, then I could say I don't have damping on the third, or I could change the damping values, it doesn't matter. The only thing is that the solutions, right, would, if I have to account for damping, I have to use the actual solution with damping for free vibration. So in order to do it more quickly, let me just say that none of the other modes were damped either. So if the second mode was not damped and the third mode was not damped, then we would have that y2 of t would be, what, minus 0.51 from obvious inspection, right? Times the cosine of omega 2t. And from looking at the computer here, I see that omega 2 is 20.62. So that would be 20.62t. And then the yt on the third mode would be 0.82 times the cosine, and then I see here that that is 27.12 t, at which point we've got the three amplitudes of the modes. Now, if we now want to say what is the response of this building, let's see, I should write it here. So what is the actual response exact due to this free vibration? Well, Qt is equal to phi y, right? Which is the sum of phi 1 times y1 plus phi 2 times y2 plus phi 3 times y3. So let's be explicit. Phi 1 is equal to 0.28. It's equal to 0.52, and the last entry is 0.62, and y1 is 0.28 times the cosine of 6.60 t plus the second mode is equal, well actually since it's going to be negative, let me just go like this, minus, what is the second mode? Minus 0.51, minus 0.3, 0.75, and then of course I already accounted for the minus, so I'm writing here 0.51 times cosine of 20.62 t, and of course plus, and I won't write it because I ran out of blackboard and it's obvious, the third mode, which would be 0.82 minus 0.37 and 0.25 multiplied times y3 of t. And here we would have then the exact solution for the free vibration of the building, in which the initial condition was 1 at the first coordinate, 0 in the others. So what is going on the first level is whatever is on this row. What's going on the second level is on this row. What's going on the third level is on this row. Okay? All right. So let me close this one. And let's continue with, let me see what's in the agenda that I wrote here. Where is it? Excuse me, give me a second here. Okay, so the next thing I want to cover is, we said that the equation that we just developed requires that the damping matrix share the eigenvectors, not the damping matrix, m to the minus 1c, right? M to the minus 1c and m to the minus 1k must have the same eigenvectors, right? If these two matrices have the same eigenvectors, then they commute. As we proved, m to the minus 1c multiplied times m to the minus 1k is in this case equal to m to the minus 1k multiplied times m to the minus 1c, and that is how we can if we had a damping matrix, check it directly whether it was classical or not. If this is true, we say that C is classical. Now, notice that when we are doing model analysis, we actually don't ever need to have a C matrix. Why? Because if we are going to do model analysis, we start with the equation already in model coordinates, yj double dot, right, plus, and this part, we just specify the damping. We don't have to know how we got to this point from the C. We just simply say, this is it, right? We needed the stiffness and the mass because that's the only way we can get the J's and the mode shapes, of course. But we don't ever need to explicitly have, what was this side? Phi J transpose, right? B2. We don't explicitly need to have, sometimes I'm using this phi, sometimes the other, it doesn't matter. So I don't really need a damping matrix to be able to specify this. I'm just simply saying, or we are simply saying, look, I would like to have the simple situation. The simple situation is that the damping matrix is classical, okay? Do I know that it is classical in reality? No, I don't know. But if it were classical, the analysis would be simplified because we can get to the nice model equation like this. So we just simply say, in the large majority of situations, it is acceptable to make that assumption, and then we don't ever need a damping matrix. We just specify the damping ratios. Okay? These are called the damping ratios, right? So if we're going to do an analysis with 5 modes, even though the structure may have 20 modes, but we're going to approximate the solution with 5, then all we need to do is make a decision as to what are the 5 damping ratios that we're going to use, right? Notice that the model of classical damping is very parsimonious, is very compact, because all I need, even if I want to do the complete, all the modes, all I need are n numbers, right? Imagine, let me be more clear. Let's say that we have a 4x4 system, right? So 1, 2, 3, 4, then 3, then 2, then 1. So the damping matrix will be symmetrical. But in a 4x4, how many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So you need 10 numbers to specify the damping matrix. But to specify the damping ratios, you would only need 4, because there's only 4 modes. So the model of the damping ratios requires only 4 numbers. Specifying the damping matrix will require 10, okay? In reality, you can see that if this is n, that was 4, but this would be something like n plus 1 times n over 2, right? So for 4 we get 5 times 2 is 10, exactly. So in general is n plus 1 times n over 2, where n is the number of degrees of freedom, while in the case of the damping ratios, we only need n. So if n was 100, now we're talking about what? 101 times 50, right? So now we're talking about 1010 times 5, so that's 0505. So to specify every entry in the damping matrix in a 100 degree of freedom system, we need 5050 numbers, right? While if we specify the damping ratios, is only 100. So it's obvious that the classical damping model is very parsimonious. It can be specified with only a few numbers. Now, there are instances, however, where we do need an explicit damping matrix. That is, it's not sufficient to just say the damping ratios are this. We do need a damping matrix. When is that the case? That is the case, for example, if the problem is not going to be solved using model coordinates. it may be, as I said, there are some problems in dynamics, some situations in dynamics, where it is more efficient to solve the problem without going to model coordinates. You might just want to integrate the equations in their original form without transforming them to modes. When is that true? Well, usually it is in problems that have many, many degrees of freedom and that are going to be solved for a very short amount of time. So the effort that it takes to calculate the modes, just simply, it's much more than the effort that it takes to actually integrate the equations for that very short amount of time that you need. Be that as it may, the other application that is extremely important in practice is that there are many problems in structural dynamics in which the problem is going to be solved into the nonlinear range. Let's say in earthquake engineering, right? You're going to do nonlinear dynamics. So if you're going to do nonlinear dynamics, model analysis is no longer applicable because model analysis is based on superposition. So you're going to have to integrate the equations. And in order to integrate the equations, you're going to need a damping matrix. So in a nonlinear problem, let's say at least in civil classical situations, it would simply be the fact that this term here, instead of being the stiffness matrix times Q, is just some function of Q, right? This would still be B2 times Ft, right? But this is some function of Q, meaning that when we know the displacements, we know the resistances, but it's not the stiffness times the displacements. This could be some nonlinear something here, okay? In these cases, we cannot do model analysis and we actually need a damping matrix. Therefore, what I'm going to show you right now in the next few minutes is how we actually formulate a damping matrix when the damping matrix is necessary, or how we can do that. So let's begin by in the following way. Let's call this how to define an explicit C. Now, the equations of motion, I could jump a little bit ahead, but I'm not going to because I think this would be useful. If I start with the equations of motion like this, we've already now seen, right? We've seen that the model substitution is this, right? So instead of going through the eigenvector and the m to the minus 1 and everything, let me just simply put that in here. So if we put that in here, we get m times phi times y double dot plus c times phi times y dot, these are all the modes, plus k times phi times q equals B2 Ft. Now, I recognize this thing and I say, well, if I pre-multiply this matrix by phi transpose, then I can get phi transpose times m times phi multiply times y double dot plus phi transpose times c times phi multiply times y dot plus phi transpose times k times phi multiply times y equals phi transpose, all of them, times B2 times Ft, right? Now, if the modes are mass normalized, we already agreed and we have proven that this matrix is just the identity, right? So for mass normalized modes, this just becomes the identity and this equation has y double dot. Now, probably, I don't know if this will be immediately obvious or not, but in the derivations that we did to show this, it also follows that phi transpose, well, yeah, now I remember, yeah, we did it. Remember that in the mole equations, this just becomes omega squared, right? Therefore, phi transpose k phi is just omega squared. So this is a matrix of the lambdas, right? So we have here, if you'd like, you know, omega 1 squared, omega 2 squared, etc. times the y, right? Right-hand side is not important right now. So the point is that this matrix, phi transpose C phi, when the phis are mass normalized, is the matrix that we have called, right, what? 2 omega 1 times the damping of the first mode, 2 omega 2 times the damping of the second mode, etc., right? That matrix goes times y dot. Therefore, right here in this parallel, we have a way to calculate the C, if we need one. Because we can then say phi transpose times the damping matrix times phi should be a matrix which is diagonal and that contains the product of 2 times the frequency times whatever dampings we want. Now let's call this matrix DC, where DC is just 2 omega 1 psi 1, 2 omega 2 psi 2, etc., right? C2. So you decide on the damping ratios, that means you decide on this matrix. Now, once you have that matrix, if you now wish to get the damping matrix, it follows by immediate substitution that if you post-multiply by the inverse of the mode shapes, and you pre-multiply by the inverse of the transpose, then you've got a damping matrix, right? So this would seem to be an expression. But again, we fall to the same discussion of before. We don't like to have this because these inversions are, you know, cumbersome. It's better to see if we can get rid of them. So we do that again by taking advantage of phi transpose and phi. Since the modes are mass normalized, we've decided to do that for convenience, is the identity. So from here we've already developed the formula and have used it now several times, that phi to the minus 1 is phi transpose m. But from this we can also find that phi to the minus transpose on both sides is just m times phi. Therefore, if we make these substitutions here, we get the following expression for the damping matrix. Phi to the minus transpose is m times the modes, then comes the DC matrix, and then comes the phi to the minus 1, which is the phi transpose times the mass matrix. Okay? So this is a convenient equation that doesn't involve any, what do you call it? Doesn't involve any inversions, right? Now, these equations can also be written, if you like this. C would be m. We leave this first m, and then we look at this term. So if you look at that term, that's like take a mode here, multiply times a number, multiply times the transpose of the same mode. So you can say here that you have a summation of phi j, right, multiplied times phi j transpose, that gives you a rank 1, multiplied times dc, which is 2 omega j times the damping j, right? And this is from j equals 1 to the number of modes, then times m again. Now, you would ask, what is the difference between these two things? And the answer is none. There's no difference. but there is one reason why people like to write it this way sometimes, which is that if you only have, let's say you only have not all the N modes, but you only have Q modes, right? So if you only have Q modes, if you only have Q less than N modes, which you've calculated, you can of course calculate it from here as summation from J equals 1 to Q, because that's all you have, of the phi J transpose times 2 omega J psi J close, and then multiply times the mass again. Okay? Now, you would say, but what do I get when I do this? Well, if you look at the equations that I just erased, this is equivalent as simply saying that the damping in all the modes that are not in this sum is 0. Because if you go to the original equation, C equals, M whatever, when you look at the D, if you were to put zeros after the Q term, if this was 2 omega Q psi Q, if you were to put zeros afterwards, I'm sure this is turning out too small. Let me make it a little bit bigger. What I mean is that, if you have 2 omega 1 psi 1, and then 2 omega Q CQ, and then you put zeros for everything else, the exact matrix is just what you get by summing Q terms of this part. So it is important to remember that if you get an explicit damping matrix and you form that explicit damping matrix using this procedure, and you only use the first whatever number of modes, you have actually put 0 damping on the modes that you have not computed. So if you are now going to solve the problem in numerical integration of the equations of motion, you have to keep in mind that you have placed 0 damping on the modes above, let's say, even if we do it linear, right? In the modes above Q, you have put 0 damping. All right, now that's a general form. There are other forms to make the damping, to form the damping matrix. Let me see. Let me see if I want to go into a lot of detail in that. There is another form, I guess, that it is important for you to be aware of, and it is this one. Assume that the damping matrix, this is a particular case, what we saw there was a classical damping, right? Classical damping, you can specify as many modes as you want. This one is going to be a simplified version of classical damping, a particular case. Assume, for example, that the damping was specified to be a combination of the mass and the stiffness. Let's say you postulate that. Well, remember, for the damping to be classical, all we need is for the modes transpose times the damping matrix times the modes to be diagonal, right? Now, if I put the C of this form, it should be obvious that what we get is alpha times the identity, right? Because phi transpose M phi is just the identity, and you get the alpha, plus beta times what? Phi transpose K phi, but phi transpose K phi is the matrix of omega squares, okay? Where this matrix lambda is just omega 1 squared, omega 2 squared, etc. Now, this is diagonal and this is diagonal. Therefore, it's obvious that this form of Z is classical because it leads to a diagonal when we do this, right? Now, in this way, we only have 2 parameters that we can control, alpha and beta. All we can say is, how big is alpha, how big is beta? When we make those two decisions, we have a damping matrix. You can see here that we're really going, we don't even want to specify the damping in many modes, we just want to say two numbers. And with those two numbers, we want to specify the damping matrix. And some computer programs accept this form from the beginning. And this is called Rayleigh damping. Or sometimes it's called proportional damping. Of course, Rayleigh damping or proportional damping is just a special form of classical damping, right? Because the matrix decomposes. Now the question is how to get alpha and beta. Well, look at it this way. This matrix here is equal to 2, let's see, how do we do this? No. Let's say we look at one entry here, so this is 2 omega, let's say we look at mode J. So if we look at mode J, this matrix here should be 2 omega J times the damping J, right? And on the right side, on the Jth row, we would have alpha, and we would have beta times omega J squared, right? Now let's look at, so I have one equation but two unknowns. Since I want to have a way to fix the two unknowns, I want another equation. So let's say I take another mode, and so I take 2 omega k times the damping k is equal to alpha plus beta times omega of the damping, omega of the mode k squared. Now that's easy because now I have two equations with two unknowns, right? And so I can decide to solve these equations like this. I can say that 1 and omega j squared and 1 and omega k squared multiplied times alpha and beta, right, is equal to whatever I see on this side, which is 2 omega j times the damping j plus, and the other one is 2 omega k times the damping in k. So that's it, right? I have this very simple two equations with two unknowns. So in Rayleigh damping, what I have to decide is how much damping do I want in two modes. So I can choose the first and the second, the first and the last, the fifth and the sixth, whatever you want. But